So here is our Sebastian, who will tell us about designing an intuitive framework. Complex pipelines in Spark. Sounds like a little bit big data for me.
Yeah.
Yeah? So welcome.
Thanks. Can you hear me properly? Yeah. My name is Sebastian. I'm a senior data scientist at a Finnish consultancy firm called Avois. And I will talk to you about how to design an intuitive framework for complex pipelines in PySpark. So the agenda for today is first a brief introduction to pipelining and to PySpark and a problem description. Then I'll move on to define some abstract terms, which is called flows and dogs, which are used to pipeline jobs. And then I want to talk to you about the DataFrame API and Spark SQL, which are two concepts in Spark and PySpark, which you can use to do data manipulation. And throughout the talk, I'll briefly mention some foundational frameworks which you can use and build upon. But before I start, I want to shout out to some of the authors of this talk, which is me, myself, Lasse, who is in the back here, Eric from our company, and Xavier as well. So let's begin. So Spark wants to define themselves as a unified analytics engine for big data processing with built-in modules for streaming, SQL, machine learning, and graph processing. So if you haven't heard about Spark before, this is the short introduction I will give you today about what Spark is. And this talk will focus on the SQL and machine learning module in particular. Then PySpark is basically just a library that binds the core functionality of Spark in Python. So think of it as a library or interface towards the core functionalities of Spark. And some common use cases for Spark and PySpark are to build complex pipelines for batch processing, reporting and analytics, and predictive modeling. So a more in-depth definition of use cases would be to load some data into a database. This is commonly referred to as ETL, extract, transform, and load. So you have data coming in from some various data sources. Then you want to transform the data into some analysis-friendly format, load it into your data warehouse, where you can do analysis on your data. And of course, you want to build aggregates on your data. Let's say you load some transactional data into your data warehouse, which contains like a customer key and a transaction key, maybe some spend, what was the spend on this transaction. Then you want to build an aggregate saying what was the total spend last month, or what was the total spend for this customer last year. And then you probably also want to build aggregates on your aggregates. So if you build your aggregate saying this is how much this customer spent, then you can build an aggregate on that to get the total spend of your company if you sum up the individual spend of all customers. But probably what you will be after is predictions. So you probably will need to build predictive models that can continuously give you predictions on, let's say, how much the customers will spend in the future. And that's what will bring you business value. And in this example here, to the left, we see a quite complex pipeline. It's not unusual to have pipelines like this, where at the end right, you might have your predictive model. And when you go backwards towards the left, you have your aggregate jobs, which aggregate data. And at the left side, you have your ETL, which loads data from a lot of different sources. So when you trigger this job, it will execute basically from left to right. But what you want is the output on the right-hand side. So it easily gets very complicated. So in order to manage this, I want to pose the problem here. What do you need to solve to be able to build these pipelines and to manage them and overview them? So first of all, there's the issue of dependency management, because you need to load the data before you can do aggregates on it. And you probably need to do aggregates before you do your predictions. So there is a natural dependency between tasks. So what is required here is a very intuitive and dynamic way to both manage and overview the dependencies of your tasks and your jobs. And I would also like to add that it should be really, really easy to add new tasks to your pipelines. And you shouldn't need much Python code to add a job. Preferably, you should need no code at all. But it should also not affect existing jobs. You shouldn't be able, if you want to add a new task to your pipeline, you shouldn't need to change other tasks to compensate for that. So it should be this plug and play, basically. And separation of key concern is very key here. So when these pipelines grow and become very, very large, the responsibility needs to be very well separated between tasks and different functionalities of the systems. And I will show you some examples of this later, so hang on. So I want to start off basically by defining some concepts, which I think is very good to have and to think about when you're building pipelines, especially in PySpark. So the first definition is a task. And the task is the smallest and core component, which is responsible for executing very well-defined and separated business logic. And in this example, I took loading a CSV file into a database table. That's one task. It's very well separated and defined. And the flow I have defined as a set of tasks or abstractions of tasks that is executed in a linear series where each task is dependent only on the previous task or no task at all. So in this flow, T1 would be executed first, which might be to load some CSV data. Then T2, T3, T4 is executed. So I like to think of this as a flow because it's flowing from left to right. So that's one way to abstract a series of tasks into a more intuitive concept. And if you would like to implement this in a very naive way in Python code, this would be how you would do it. So you create a class called flow, which takes a set or a list of tasks, basically, and executes them in the order. And then you can define 4 tasks, as the example previously, chain them in a flow and execute it. However, this is not a flow because of the highlighted definition. Each task should only be dependent only on the previous task. So in this example, T3 is dependent on 2 different tasks. And hence, this is not a flow. But you can create another abstraction where you encapsulate T1 and T2 into this TD, let's call it. And then TD, T3, T4 is or can be considered a flow. The next concept is the DAG, which is a directed acyclic graph, where each task is executed with respect to its dependencies, and where each task is dependent directly on one or multiple tasks. So in this example, T1 has no dependency. Both T2, T3 is dependent on T4, and T1 is dependent on T2 and T3. So if you were to execute T1 in this example, you first need to execute T2 and T3, which both need T4 to be executed. And this is how you build basically a graph of your jobs. And to implement this in a slightly naive way in code, you create a task which takes a list of dependencies. Then you have your execute or underscore execute function, where you put your actual logic. And then you have your execute function, which just executes the dependencies and then execute itself. And in this example, we have T4, T3, T2, T1. And we have here the specified dependency in this example. And then you can do execute on T1 and everything will execute in correct order. And what's good about this is that you can combine these concepts to create very rich and complex but still intuitive pipelines. So in this example, we have two flows. T1 to T4 is a flow, but TF itself is a flow. And here, TD1 is a cyclic graph. And you can combine them further, and it can look like this, that you have an overall flow which executes T1 through T4. Then you have another flow, and in that flow you have a dog. And if you press execute on F, everything will be executed in the correct order. So you don't have to think about the dependency management here. Or rather, your code does it for you. So if we split this in 5 panes, we can see how we would implement this in this naive way. So at the bottom, in the bottom here, we have TFD4, which we denote by number 1. And in the code, we just create TFD4. Number 2 is the two tasks dependent on FD4. So number 2, we have TFD2 and 3, which both depend on TFD4. If we go up one level in the graph, we see that we have 4 tasks, TF1, D, 3, and 4, where TFD is dependent on both the tasks in step number 2. And at level 4, we have 4 tasks, where one of them is a flow. And at the top level, we have this final flow, which executes T1 to T4. And then we can execute the flow. So this is very abstract, sorry for that. So I will take a more concrete example, so you can actually understand what this would mean for a company. So let's say we have an online web shop which wants to do predictions, let's say for customer spend. And in this case, the flow might be implemented as this. So we have some kind of predict spend flow, which extends flow. And in the init, it's just change 4 different tasks. And the tasks in this example would be to load some customer data, load some transaction data, build a data set, and then predict some spend. And as you see here, data set itself is a flow. So if we go deeper into oh, it's not highlighted, sorry. If we go deeper to the level below the flow, we can look at the code like this. So we have the customer data ETL, which is a task with no dependencies here. And it will extract some data from a source, transform it, and load it into a table. And the same thing for the transactions. Then we have the data set, which is a flow again, which will chain 4 tasks. One which creates features for the customers, one which creates features for the transactions and the products, and then combines them all together. And then we have the prediction task, which predicts something. And at the next level, we have some customer features, transaction features, and the transaction features in this case is a task, which is dependent on 2 tasks, the spend per customer and the spend per product. Then we have our product features, and then we can combine all our features. And now to the bottom 3 tasks, which is the last piece of the puzzle here. Then we have spend per customer, which is dependent on customer spend per product. We have spend per product, has the same dependency. And then we have the last task, which is customer spend per product. And finally, we can execute all this by creating a new predict spend flow and execute it. And everything will load the data, it will create all the features, execute the dataset flow, and then predict everything. Just a quick recap here. So we have this where the top flow is to load transaction, load customer data, create a dataset, and then predict something. At the level below that, we have the dataset flow, which is TF1 to TF4 here. And in the dataset flow, we saw that we did some customer features, some transaction features, product features, and then combined them all together. And in the end, you can execute all of it by just pressing one button, basically. However, there are some existing frameworks for this already, so you shouldn't implement this by yourself. Instead, you should use some existing framework and build upon them. And just to name some of them, I think the most famous ones are Apache Airflow, which I recommend, Luigi, which is a pipelining framework created by Spotify, and also Azkaban, which was created and used by LinkedIn. So, a lot of what I've just showed you is related to data management and data manipulation, basically. So in PySpark, you basically have 2 ways, or you have 3 ways, but the third one is basically legacy by now. And the 2 ways are the DataFrame API and the Spark SQL. And the DataFrame API is very similar to Pandas, which is a Python package. If you have used it, you're probably familiar with the DataFrame API code in PySpark. And you have your Spark SQL, which is basically standard SQL code. I will show you some example of this. So what I want to highlight here is that there is a clear syntactical difference between the 2, even though they solve the same thing. However, I believe that Spark SQL is much more intuitive than the DataFrame API, which I would like to demonstrate with an example in just 1 minute. However, there is no performance difference because both of them is parsed into the same DOG, basically. However, I want to stress this part that there is a difference in intuition because SQL is widely used for data processing and generally more recognizable. So a lot more people will understand SQL than this DataFrame API in Python. So let's make this a bit more concrete. So let's say we have this table with some customers, and for each day we have how much each customer have spent. And the problem is to calculate the within month cumulative spend of each customer each day. So the result, and save it to a table. So the resulting table should look like this. So you have your window, which is the month, and you want to calculate the cumulative spend within this window. In the DataFrame API, in PySpark, you would solve it like this. You would create a DataFrame of your Spark.table, where Spark is your Spark session. And then you would select the columns of interest. Then you would add a column with the with column command. You would name it cumulative spend. You will do a sum function over the spend column, over a window partition, partitioned by the customer ID and the date truncated to a month, and then order it by date. And then you write and save it to a table. However, in Spark SQL, you would solve it like this. And probably this would ring a bell for more people than the previous example. So this is basically standard SQL, which most of you have seen, I believe, where you select your columns, you do a sum over a column, over a partition, and order it by date. And I would argue that the Spark SQL example is a lot more intuitive. And this is a really simple and small problem. So when you're creating these huge and very complex aggregations, DataFrame API gets unreadable very quick. So I would suggest that you use Spark SQL instead. Again, there is no performance difference because they are parsed into the same DOG and executed by the Spark core. However, if you do your data manipulation in SQL, you can extract all of that into SQL files and keep that outside of your Python code. And then let Python do basically the binding, which executes the SQL in the correct order, etc. And also do file manipulations, etc. In this way, when you look at the Python file, you know that there will be no data manipulation here. There will be just file system manipulations, file imports, etc. And then you have your SQL files. On the other hand, when you look at them, you know, okay, here is some data manipulation going on. In this way, you get very clear division of responsibility, that SQL is responsible for data manipulation, while Python is the glue and the code that does imports of file and file system manipulations, etc. And lastly, I would like to discuss briefly Spark versus PySpark. And by Spark, I mean Spark in Scala instead of Python. So I think there are a lot of myths saying that PySpark is so slow, you shouldn't use PySpark, you should use Scala Spark, etc. So if Spark then is the F1 car, is PySpark then the go-kart? And I would say no, that there is no significant difference in performance unless you are writing your own user-defined functions or using the RDD-based API. But today and going forward, the Spark core functionality is so rich that 99% of everything you do, you would do with the Spark core functionality. So there's actually no need to write your own UDFs or go through the RDD API. So avoid this at all costs. And then I want to round up this presentation with a few takeaways. So if you're building your own pipelines and you want to use PySpark or any other tool, I would say that this is what you should remember. So you want to build predictions which require aggregations, which require some kind of ETL. You need to load the data into your analytical environment. And this will yield very complex pipelines very quickly. And then what is key is intuitive code when you build and manage your pipelines. And the simplicity of adding new logic is what will yield exponential value for you. So if you need to spend 0% of your time for maintaining your pipelines and just can add new functionality all the time. And anyone almost can add new functionality. You will see that your business value will grow exponentially. And I would like you to remember to split and encapsulate your business logic into smaller components, which is tasks. And then abstract those into more intuitive concepts like flows, where you have a series of tasks, or a dog, which is a graph with dependencies specified. And utilize existing frameworks, so don't reinvent the wheel. Instead, build upon the existing frameworks where you wrap the framework, let's say Airflow, create your flows and your dogs, etc. Then you will also get this very nice graphical user interface where you can monitor your tasks. And lastly, I would say, if you're using PySpark, go for Spark SQL when you do any kind of data manipulation. It's much more intuitive. And there is no performance loss between DataFrame API and no performance loss for PySpark, I would say, unless you're doing some crazy stuff with Lambda functions, etc. And some shameless advertising. If you think this sounds interesting, we are always looking for talented people. So surf in, take a picture if you're interested. And I would like to say thank you for listening. If you have any questions, please. Otherwise, you can find me at email.
Sorry, thanks for a good talk. So this is obviously a really great way to empower non-engineers to do great analysis and sort of add value to the company. But as you do this, when you make it simple to add these tasks and add this data manipulation, how do you do testing, validation? How do you add that to your pipelines so that people can actually... I mean, one problem we've seen is that people deploy bad tasks, which steal a lot of resources. So how do you sort of layer your QA work so you don't deploy bad stuff in production too often anyway?
Yeah, that's a really good question. I think testing when it comes to SQL is really, really hard because you need to mock like a lot of data to test all of your logic and so on. And I have no super good answer to that, except have a good pipeline for deployment with your development environment, test environment, where you stress test all your jobs in a real life scenario or production-like scenario before you deploy them to production. So the answer would be not related to PySpark, but rather like a good deployment policies.
Thanks.
Hi, thank you for an excellent talk. I was wondering why the distinction between a flow and a DAG, because it would seem that the flow is a special case of the DAG.
That is true. A flow is a special case of the dog. However, I want to make a separation between the two because a flow is a much more simple abstraction than a dog. So if you can get away with a flow in your pipeline, I would recommend using a flow instead of a dog. Because if you have a dog, which is a flow of, let's say, 20 tasks, then the first task needs to specify the dependency of the second, then the third, and it quickly gets unreadable. However, a flow is much more easier to overview than a dog.
Thank you.
Okay, then thanks again for the amazing talk from Sebastian.
Thank you.